we've seen that just because you have an initial value problem does not guarantee that the initial value problem has a unique solution. And that's something that we would sort of like, just because, initial value problems will often be describing physical situations, and physical situations usually have a deterministic outcome as long as you ignore quantum mechanics. So we would like to know, when is it that initial value problems have a unique solution? And that's actually a pretty tricky question to answer, but here's a partial answer to that question. And I'm not going to fully justify why this fact about differential equations is true. You're kind of going to have to take my word for it. So we're going to concentrate just on first order initial value problems. So initial value problems where our differential equation is a first order differential equation. And in these kinds of differential equations, we're going to concentrate actually on explicit first order equations where the derivative shows up by itself on the left. And for this kind of differential equation, you can always write it as dy dx equals some function, some combination of x and y, together with our initial condition, which is y of some x value is some y value. Okay, so there are sort of two questions, and first is, when can we be sure that a solution even exists? And that's what the first part of this theorem is talking about. So it all depends on the properties of this function f in the xy plane near your initial condition. So here's our initial condition, x naught, y naught. Okay, now this function is a function of two variables, and to be sure that a solution to the initial value problem exists, what we need to be able to do is find or know that there is some rectangle that contains the initial value. So this rectangle, we're going to call it R. This rectangle contains the initial value on the inside of the rectangle, not on the edge. And the function f is continuous on this rectangle. Okay, so if you need names for all of these values, you can say the rectangle goes from A to B in the x direction and from C to D, say, in the y direction. Okay, so if there is such a rectangle around your initial value where this right-hand side function is continuous, then there exists at least one solution to the initial value problem. And also that solution is guaranteed to exist for some interval of x values between a and b. So it might not actually be for the entire interval of x values. Your solution might look like this and wander outside of this good rectangle before you get to the end of the interval from a to b. But there's some interval of x values where there's a solution, at least one solution. Incidentally, this theorem, it can say that a solution exists, but it can't say that a solution doesn't exist. So it can say, yes, a solution exists, or I don't know. It can't say no. Okay, so that's for the existence piece, but what about uniqueness? So that's the second part of this theorem. You just need to add one extra assumption, which is that not only is the function f continuous, but also its derivative with respect to y is also continuous. And then your solution that we knew existed before is guaranteed to be unique. Now, if you haven't seen these symbols before, hopefully they look reminiscent of a derivative, and that's because they are a derivative. This is just the derivative of f, where you treat y like the variable, and you treat x like a constant. So you just pretend x is a constant and y is a variable and take a derivative with respect to y. This is called a partial derivative. And we'll see some examples in a little bit. Okay, so As you can see, whether they're part 2 also can say yes, the solution is unique, or I don't know if it's unique. It can't say that the solution isn't unique. So you can see that whether there is a unique solution all depends on the properties of this function on the right that really is describing the differential equation together with the initial condition. So the initial condition is a key piece of whether a solution exists and is unique, because you have to be able to wrap the initial condition in this sort of safety rectangle to know that a solution exists if the function is continuous on that safety rectangle and is unique if the derivative with respect to y is also continuous on that safety rectangle.